start with one new topic in our syllabus called as the differential equations. Now up till now we have studied some equations, like we could have equation of line, equation of plane, or for that matter some quadratic equation, some polynomial equation and so on. Again the word equation comes into picture, and this time equation means it is a equation which involves some differential coefficients. The equations which involve the differential coefficients or the differentials is called as a differential equation. There are many practical applications where we will be talking about rate of change of, or it could be rate of change of. These type of terms, they will always involve the differential coefficients or only the differentials. And so the differential equation, it can be formed from some equation which is available in terms of x and y. For example, if we have the equation as x square y minus 2xy cube plus y raised to 4 equal to say 4, then differentiating it with respect to x, we get 2x into y plus x square dy by dx minus 2x into 3y square dy by dx minus 2y cube plus 4y cube dy by dx equal to 0. Now this becomes a differential equation. Now when we talk of partial differential equation, then the differential coefficients which are involved, those will be the partial coefficients. We are aware of the fact that partial means you will be keeping one of the independent variable as constant and then differentiating with respect to other. For example, if z is equal to x square y minus 4y cube, then we cannot find anything like dz by dx, because z happens to be function of x and y. Instead of that, we find dabba z by dabba x, that is differentiating z with respect to x, treating y as constant, and the value will come out to be differentiation of x square as 2x and y as it is, whereas the second term will be straight away 0, because we are differentiating with respect to x and y is constant. Similarly, we can find dabba z by dabba y, where we will be differentiating with respect to y and treating x as constant. So in the first term x square is constant, differentiation of y is 1, minus 4y cube is differentiated as 12y square. So if the terms like dabba z by dabba x or dabba z by dabba y are involved, then the equation will be called as a partial differential equation. Now there will be few more terms which will go along with the differential equation, and those terms are: number 1, it is called as the order of the differential equation, and number 2, it is the degree of the differential equation. Now order of a differential equation is defined as the order of the highest derivative. It is the order of highest derivative which appears in the equation. Whereas the degree, when we talk of, degree will be corresponding to the degree of the highest order derivative. So we have two more terms. One is called as the order of the differential equation and other is degree. But of course just these definitions will not be of any use. Let us take actual example and see what do we mean by the order of the differential equation and the degree of the differential equation. Say the equation is d raised to 4y by dx raised to 4 minus 3x square d square y by dx square plus 4xy is equal to 0. Now this is a differential equation because it involves the differential coefficients like d raised to 4y by dx raised to 4 or d2y by dx square. Now the highest order derivative in this case is going to be d raised to 4y by dx raised to 4, and this is second level differentiation. So the order of this differential equation will be the order of highest derivative, so order is going to be 4. And if we talk of the power or the degree of this particular differential equation, then it is going to be the degree of the highest order derivative, so it is going to be 1. Consider another example. Say d2y by dx square minus 4 dy by dx bracket cube plus 7x square y equal to 0. Now in this case, order of the differential equation is 2 and degree of the differential equation, many times you confuse that this is the derivative that we have and its degree is 3. It doesn't mean that the degree of highest degree in the particular equation, it is the degree of the highest order derivative. So in this case the degree will be still 1. In case of d cube y by dx cube bracket square minus 4 dy by dx plus 7 d2y by dx square equal to 0. In this case, the order of the differential equation is 3 and degree of the differential equation is 2. If we have the equation as dy by dx is equal to 4xy divided by 1 plus dy by dx, then the order is 1 and degree, if you write it as 1, that will be wrong because you cannot have the denominator for such an equation. You will have to cross multiply. It will be 1 plus dy by dx multiplied by dy by dx, giving us 4xy, and if you multiply you will find that it is dy by dx bracket square plus dy by dx equal to 4xy, and so order of this differential equation is 1 and degree of this differential equation is 2. So we have seen what do we mean by a differential equation, and now let us proceed further and talk about what is known as the solution of a differential equation. The solution of a differential equation is a functional relation among x and y without involving any differential coefficient. That means we are required to eliminate the differential coefficients which appear in the given equation. For example, let us take a case of simplest equation, simplest differential equation, which could be of the type, say, dy by dx is equal to x square. So if the equation is of the type dy by dx is equal to x square, it will be a differential equation, and then to solve it we will write it as dy equal to x square dx, and then integrating both sides we will get it as integral dy equal to integral x square dx plus constant of integration, and ultimately we get it as y equal to x cube by 3 plus constant, which is known as the solution of that differential equation. So when we say solve a differential equation, we will have to eliminate the differential coefficient which is present in the given equation. Let us consider few more examples. What will happen if the given equation is of the type dy by dx is equal to x y? Now when we try to solve this equation, then we will be writing it as dy equal to xy dx, but then the integration will be rather problematic because you have got xy dx term on one side. Whereas if we could separate out the variables and write it as dy upon y equal to x dx and then proceed with the integration, we will get it as integral dy upon y equal to integral x dx plus the constant of integration, and dy upon y will be integrated as log y equal to x square by 2 plus constant, or if we raise both sides to power e, so it will be e raised to log y, which is equal to e raised to x square by 2 plus constant. So it will be y equal to e raised to x square by 2 plus c, that can be written as into e raised to c, or the solution can simply turn out to be y equal to c e raised to x square by 2. Here for e raised to c I am again writing c, because any term that is constant of integration, which could be e raised to c, which could be c, which could be c square, it could be log c, it could be c cube plus 1, all of them can simply be replaced by c at any moment. So as we have the look at the solution of differential equation, we obviously get the very first form of the differential equation called as the variables separable. It will be that equation, it will be that differential equation in which we can separate out the variables, that is x on one side and probably y on the other side. So the form of the first type, which is called as variables separable, the form of the differential equation can be written as f1x dx plus f2y dy is equal to 0. That means you have got all the terms of x and a differential coefficient dx multiplying it, and all the terms of y multiplied by dy equal to 0. The solution in this case is given by integral f1x dx plus integral f2y dy equal to constant of integration. So we come across the first type of differential equation. The first method by which the differential equation can be solved is known as the variables separable. Obviously, the given equation will not be given to us in the form where the variables are written in the separated manner. Probably we will have to take some terms common and then rewrite the equation in the variable separable form and then solve it. For example, the first problem that we have, it is given as y minus x dy by dx is equal to a into bracket y square plus dy by dx. We want to solve the given differential equation. For this, we first of all multiply by a on the right hand side, and then in the next step we will be collecting all the terms of dy by dx on one side. So it will be y minus ay square is equal to a dy by dx plus x dy by dx. So it can be written as, on the right hand side, as a plus x into dy by dx, whereas the left hand side will be y into bracket 1 minus ay. Now to proceed with the solution, we will have to separate out these variables, and it will be written as dx upon a plus x is equal to dy upon y into bracket 1 minus ay. And therefore we can conclude that it is the form called as variables separable. So as we separate out the variables, we get it as dx upon x plus a equal to dy upon y into bracket 1 minus ay. In variable separable, we are required to integrate both sides, and there will be constant of integration which will be introduced. Will be written as plus c. The left hand side is directly integrable, that is integral dx upon x plus a, denominator being single degree. We can very well integrate it and we get it as log of x plus a. Whereas on the right hand side, we will have to go for what is known as partial fractions. You will have to separate out the denominator. Now, when the denominator is in the single degree, the procedure to be followed is like this. We have got y plus 1 upon something upon 1 minus ay, and the actual term was 1 upon y into bracket 1 minus ay. Now to find numerator of this y, we will have to check that there are two terms. First term will be 0 when y is equal to 0. So put y equal to 0 everywhere except this term, that is the numerator of y will be 1 upon 1 minus 0. Whereas when we try to find numerator of 1 minus ay, then 1 minus ay will be equal to 0 when y equal to 1 upon a. So substitute y equal to 1 upon a everywhere except this term. So ultimately it will be 1 upon a. And so in the separated form it will come out to be 1 upon y plus a upon 1 minus ay. You can always take the LCM and check whether it results in the left hand side. So it is 1 minus ay plus a into y divided by y into bracket 1 minus ay. As ay cancels, it will be 1 upon y into bracket 1 minus ay. So this particular procedure of separating the product in the denominator as the separate terms is called as partial fractions. Of course, it is also suggested that you can go for writing the numerator as say C1 and C2 and then take LCM and then match the numerator. But so far as the single degree terms are concerned, this particular procedure will be faster as compared to anything else. So with this particular separation, we can go back to the integral and write the numerator of y as 1 and numerator of 1 minus ay as a. So the right hand side is also integrable. Integration of 1 upon y is log y, and that of a can be taken constant. Integration of 1 upon 1 minus ay will be log of 1 minus ay divided by coefficient of y, that is minus a, plus constant of integration. So ultimately a cancels here. Right hand side will be log y minus log of 1 minus ay plus constant of integration. Now we can take all the log terms on one side. So you will get it as log of x plus a minus log y plus log of 1 minus ay equal to constant. Now log minus log will be log of a upon b, that is log of x plus a upon y. So we can write the first one as log of x plus a upon y, and then we have got plus log, so it will be into 1 minus ay. So it is going to be the log of the whole thing equal to c. And therefore we can raise both sides to power e. It will be x plus a upon y into 1 minus ay equal to c. And therefore, of course, it was equal to e raised to c, which can be very well written as c. And so the final answer comes out to be x plus a into 1 minus ay equal to c into y, which is the solution of the given differential equation. So the procedure is simple and straightforward. Only thing is we are required to separate the variables. When the variables get separated, you are required to integrate, and for integration you will have to either go for partial fractions, or sometimes it is going to be integration by parts, and all the formulae of our single integral will be very well useful over here. Limits generally are not given, but some conditions like at x equal to 0, y has so and so value can be given to us, and it is for finding the value of constant of integration c. As we have got only one constant of integration over here, we will be requiring only one boundary condition to find out that constant c. Solution will be always the relation between x and y which does not contain differential coefficient or the differentials. Problem where the solution was simple and straightforward. Let us go for the next set of problems. Second problem, which is a into bracket x dy by dx plus 2y bracket complete equal to 2xy dy by dx. Third problem, it is into bracket x plus 1 dy by dx plus 1 equal to 2 e raised to minus y. Fourth, it is x cos x into cos y plus sin y dy by dx equal to 0. And the fifth one, x into bracket 1 minus y bracket complete dx plus into bracket 1 plus y square bracket complete into another bracket x minus 1 bracket complete dy equal to 0. If you observe the given differential equations, then you will find that x and y are not directly seen in the separable form. But the very first try that we can always make for solving the differential equation is to separate out the variables if possible. So let us start with the solution of the second one. The given equation is a into bracket x dy by dx plus 2y equal to 2xy dy by dx. The attempt should be to collect all the dy by dx terms on one side and all the other terms on the other side. So it will be ax as I multiply minus 2xy dy by dx will be equal to minus 2ay. We are going to cross multiply, but before that, if possible, separate out x and y. So it is x into bracket a minus 2y dy will be equal to minus 2ay dx. Now we want all y terms on one side and x terms on the other. So this particular y can be shifted as a denominator here, and x can be shifted as a denominator of the right hand side. It can be written as a minus 2y upon y dy equal to minus 2a upon x dx. As we proceed with the solution, it is written as integral a upon y minus 2 dy minus 2a, rather plus 2a, or we can write it as equal to minus 2a integral dx upon x plus constant of integration, which will result in a log y integration of 1 upon y minus 2y integration of minus 2 is minus 2y equal to minus 2a log x plus the constant of integration. For simplification, we can take the terms on one side, all log terms. So it will be a log y plus 2a log x is equal to c plus 2y. If we take a common, it will be log y, and 2 log x can be written as log of x square equal to c plus 2y. Combining these two log terms, we will get log of yx square is equal to c plus 2y upon a. This was actually c upon a, but it can be always written as c. And then raising both sides to power e, we will get it as yx square equal to e raised to c plus 2y upon a, which can simply be written as c e raised to 2y upon a. Left hand side is x square y, which is the simplified solution of problem number 2. So though the variables are not given in the separable form, we can very well separate them and then obtain the solution. Consider problem number 3. It is x plus 1 dy by dx plus 1 equal to 2 e raised to minus y. So we can write it as x plus 1 dy by dx equal to 2 e raised to minus y minus 1, which can be written as dy upon 2 e raised to minus y minus 1 equal to dx upon x plus 1. So it appears in the variable separable form now, and we will be integrating both sides, that is dy upon 2 e raised to minus y minus 1 equal to integral dx upon x plus 1 plus c. The left hand side over here is not in the integrable form, so we will have to multiply numerator and denominator by e raised to y. So it is e raised to y dy divided by 2 minus e raised to y equal to right hand side can be directly integrated as log of x plus 1 plus constant of integration. And so in the left hand side we can see that if denominator is assumed as, that is 2 minus e raised to y, if it is assumed as t, then minus e raised to y dy will be dt, that is e raised to y dy can be written as minus dt. So if we could simply adjust minus sign in the left hand side, that is we write it as minus of minus e raised to y dy upon 2 minus e raised to y equal to log of x plus 1 plus constant c. Then we have got differentiation of denominator in the numerator. So it is f dash x dx upon fx, which can be integrated as log of fx, and so it comes out to be minus log of 2 minus e raised to y equal to log of x plus 1 plus constant. So ultimately we get it as log of x plus 1 plus log of 2 minus e raised to y is equal to constant, taking this log on the other side and c on the left hand side, and ultimately we get it as log of x plus 1 into 2 minus e raised to y, log of this whole thing equal to constant, and the final solution will be x plus 1 into 2 minus e raised to y equal to constant. So in problem number 4, which is x cos x into cos y plus sin y dy by dx equal to 0. We are certainly aware of the fact that x cos x should get multiplied by dx, or it should be separated with dx, and this cos y is extra term. So we can probably say that multiplying throughout, multiplying by dx upon cos y, we will get it as x cos x dx, where cos y cancels, plus sin y upon cos y dy equal to 0, which was our stated form, that is f1 dx plus f2y dy equal to 0. The solution obviously will be integral x cos x dx plus integral tan y dy equal to constant of integration c. X cos x should be integrated by parts, that is retain first. Integration of cos x is sin x minus integral differentiate first, that is 1. Integration of cos x is sin x dx plus integration of tan y is log of sec y equal to the constant of integration c. So it will be x sin x minus integration of sin x is minus cos x plus log of sec y equal to the constant of integration. Finally, the answer comes out to be x sin x plus cos x minus log of cos y. Sec y can be written as 1 upon cos y, that is cos y raised to minus 1 equal to constant of integration c. The simple and straightforward looking problems to be attempted one after the other. Here we are quite aware of the fact that it is going to be of the type variable separable. But once we learn all the different ways of solving the differential equation, then we are not aware of the fact that the problem belongs to a particular type, and at that time these problems really appear to be very tough. So the fifth problem, as we know only one method, that is variable separable, obviously this also will turn out to be in the category of variable separable, and we will be definitely looking for separating the variables and writing the terms of x only and y only. So here the first term can be written as x dx upon x minus 1. I have already eliminated 1 minus y from here, which will be obviously dividing the second term, and the second term was containing x minus 1, which I have divided to the first term. So ultimately this can be obtained by saying that dividing by x minus 1 into 1 minus y. So we get the equation in this form, which is variable separable. And now integrating it, so x dx upon x minus 1 plus integral 1 minus y 1 plus y square upon 1 minus y dy equal to constant of integration. In the first one we will have to go for adjustment. Write the numerator as x minus 1 plus 1 upon x minus 1 dx. And similarly in the second case some adjustment will be required, because the numerator is having higher power than the denominator. Here we can separate out the first integral as 1 upon 1 minus y, but the second integral will be plus y square. Now we will have to find out the procedure by which these can be separated. One of the ways is you divide the numerator by the denominator. So it is 1 minus y 1, and it is minus y that will come into picture. You will have to subtract, so it becomes y square plus y, and to obtain y square from minus y, it will be minus y, that will be the quotient. And so when you multiply by minus y, it will be y square, and of course the first term, which is minus y. As you change the signs, this will cancel out, this will be 2y. And so we can think of writing it as 1 plus y square upon 1 minus y is equal to 1 minus y plus 2y upon 1 minus y. Of course, this particular adjustment would have been also possible by adjusting the middle term in the given integral, because we have 1 plus y square, which can be very well written as 1 minus 2y plus y square, that is adjusting 1 minus y bracket square plus 2y. It was the same adjustment that is suggested. And then to integrate this 2y upon 1 minus y, it is the similar policy that we were following on the left hand side. So the the second integral that we have can now be written as 1 minus y plus 2y upon 1 minus y dy plus constant of integration, or equal to constant of integration. And so we can proceed further. The first integral can be written as integral 1 plus 1 upon x minus 1 dx, plus the second integral can be written as integral 1 minus y plus 2 into bracket, it is going to be again the adjustment, and that will be, that adjustment can be written as 1 minus y plus 1 upon 1 minus y dy equal to constant. Proceed with the integration. 1 is integrated as x, 1 upon x minus 1 is integrated as log of x minus 1. For the second integral, 1 is integrated as y, minus y is integrated as y square by 2, plus the second last term over here in the integral form is written as minus 1 plus 1 upon 1 minus y dy equal to constant. So it will be x plus log of x minus 1 plus y minus y square by 2 plus 2, minus 1 will be integrated as minus y, and log of 1 minus y, but don't forget to divide by the coefficient of y, that is minus 1, equal to constant of integration. And so it will come out to be x plus log of x minus 1 plus y minus y square by 2 minus 2y minus minus plus, sorry, it is minus 2 log of 1 minus y equal to c. If required, you can collect all the terms of log together. So it will be x, this y minus 2y will be minus y square by 2 plus log of x minus 1 divided by, this will go as square, 1 minus y bracket square equal to constant of integration. This could be considered as the final solution. Separable. We have got the second type, homogeneous differential equations. These are rather easy to identify, because homogeneous term indicates that every term in given equation has same degree of x and y taken together. So it is very easy to identify. For example, if you have terms like x cube y or y raised to 4 as x y cube or x square y square, these terms are considered as homogeneous terms of degree 4. If you have got some other term like xy, then the overall it is not homogeneous. So here we are saying that every term in the given differential equation should have the same degree of x and y taken together. So it is not that x power of x should be equal to power of y. It should be x and y powers addition, that is 3 plus 1 4. Here it is 0 plus 4 4. 1 plus 3 it is 4. 2 plus 2 it is 4. And this is not the term belonging to it. Now when the given differential equation has this particular property, that it is homogeneous in x and y, then observe that all these terms which I have written earlier, terms like x square, y square, terms like y raised to 4 and so on, if I divide throughout by say x raised to 4, then I will get the terms as y by x plus y square upon x square plus y raised to 4 upon x raised to 4, and ultimately this will turn out to be a function of y upon x. So homogeneous equation of degree n, when throughout divided by x raised to n, will result in a function of y by x. We will be using this particular policy to solve the differential equation. f1 of x comma y upon f2 of x comma y, such that both f1 and f2 are homogeneous of degree n. Now this is obvious that both of them should have same degree, because the given differential equation can be written in the form f2 of x comma y dy minus f1 of x comma y dx is equal to 0. And as we talk of the homogeneity, then f2 of x comma y and f1 of x comma y, they form the part of the equation, and as the overall equation is homogeneous, their degree must be same. So when we consider dy by dx equal to f1 of xy upon f2 of xy, both f1 f2 as homogeneous of degree n, then we can take x raised to n common from numerator as well as from denominator, resulting in numerator as x raised to n into some function of y by x, divided by denominator as x raised to n into some other function of y by x, left hand side remaining dy by dx. So x raised to n will cancel, and you have got some function of y by x divided by some function of y by x, which can be easily written as, say, psi of y by x. Now we can make a substitution, that is, let y by x is equal to u. Therefore, y equal to x into u, and differentiating both sides with respect to x, dy by dx equal to x into du by dx plus u. We will get the given equation as x into du by dx plus u equal to psi of u. X into du by dx plus u equal to psi of u. Therefore, x du by dx equal to psi of u minus u, and then it can be written as du upon psi of u minus u equal to dx upon x, which is our earlier form, variables separable. So here we should follow the procedure. From this point onwards, we should follow the procedure of variables separable, and then get the equation in the form of u and x. At the end, we are required to resubstitute u as y by x. Let us now consider some problems on the homogeneous differential equations. We have said that it is very easy to identify such a problem. We will not be directly going for anything like variable separable. We should be first observing the given equation and check for the homogeneous nature if it is present in the given problem. If the differential equation is homogeneous, then it is better to start the solution with the homogeneous point of view. Now the next set of problem consists of, in all 5 problems, again as we are aware of the fact that after homogeneous we are learning or studying these particular problems, all of them are bound to be homogeneous, but we will have to observe each and every term. Here the first problem, which says that into bracket x square plus y square bracket complete dx minus 2xy dy equal to 0. The degree of first term additive, so 2 and 2, so degree is 2 for the first term. For the second term also it is xy, that is 1 plus 1, 2. The second equation is again homogeneous, first term having degree 1, second term the numerator has degree 2 and denominator has degree 1, so it is 2 minus 1, degree is 1, and the right hand side is again degree 1. Third equation, it is 1 plus 1, degree 2, and again these two terms each having degree 2. Fourth equation, 1, 1, and again degree 1, 1, homogeneous of degree 1, whereas the last equation is of degree 2. Let us solve the first problem. It is x square plus y square dx minus 2xy dy equal to 0. It should be written in the form dy by dx equal to. So we will write it as dy by dx is equal to x square plus y square upon 2xy. So the equation comes out to be in the form dy by dx equal to x square plus y square upon 2xy. Both numerator and denominator have degree 2, so we can take x square common. So it is x square into bracket 1 plus y square upon x square divided by x square into bracket 2y upon x. And then we will have to substitute, that is let y upon x is equal to u. Therefore y equal to x into u. Hence dy by dx will be x into du by dx plus 1 into u. Substituting, we will get x du by dx plus u, cancelling x square from numerator and denominator, it will be 1 plus u square upon 2u. Therefore x du by dx equal to 1 plus u square upon u upon 2u minus u. Take the LCM, it is 1 plus u square minus 2u square upon 2u, which will be 1 minus u square upon 2u. Now this is in the form of variable separable. We can cross multiply and get the equation as 2u upon 1 minus u square du equal to dx upon x. It is variable separable in terms of u and x. So integrating both sides, we will get it as integral 2u upon 1 minus u square du equal to integral dx upon x plus constant of integration c. Again it is in the form f dash upon f 1 minus u square when differentiated will give minus 2u. So we will adjust minus sign and then proceed with the integration. It is minus log of 1 minus u square, which is integration of left hand side, equal to log of x plus constant. So taking this log term that is log of 1 minus u square on the right hand side, we can rewrite it as log of x plus log of 1 minus u square equal to constant, and so it will be log of x into bracket 1 minus u square equal to constant, that is x into bracket 1 minus u square equal to constant. Now this is the solution of differential equation which we have got in terms of u and x, whereas the given equation contains y and x. So we will have to resubstitute u as y by x. So it will be x into bracket 1 minus y square upon x square equal to the constant. So it will be x into bracket x square minus y square upon x square equal to constant, or finally the answer will be x square minus y square is equal to c into x. So homogeneous differential equation will always result in the form variables separable. It will be always the substitution that y by x will be substituted as u, and it has to convert itself into the variable separable form. If it doesn't convert to variable separable form, then what you have done is containing some mistake. Consider the second problem, which is, as we have already said, is homogeneous of degree 1, and so we will have to take x common from numerator and denominator, and we are required to first of all write dy by dx. So it is x dy by dx plus y square upon x is equal to y. Therefore x dy by dx will be equal to y minus y square upon x, and dy by dx will be y minus y square upon x divided by x. So numerator is homogeneous of degree 1, denominator is also homogeneous of degree 1, so we will have to take x common from numerator. So it is x into bracket y upon x minus y square upon x square divided by denominator is x into bracket 1, so x will cancel out. So right hand side now remains as a function of y by x, and we will make the same substitution. Let y by x is equal to u. Therefore y is equal to x into u. Therefore dy by dx will be x into du by dx plus u. Substituting in the given equation, x du by dx plus u, right hand side will be u minus u square, so obviously u gets cancelled, and therefore the equation turns out to be du upon u square equal to minus dx upon x, which is the variable separable form. Integrating both sides, we get it as du upon u square equal to minus integral dx upon x plus constant of integration. Integration of 1 upon u square, that is u raised to minus 2, will be u raised to minus 2 plus 1 upon minus 2 plus 1, or you can directly remember the formula that integration of 1 upon u square is minus 1 upon u. So this is minus 1 upon u equal to minus log x plus constant, and so we can write it as 1 upon u is equal to log x plus constant, and substituting u as y upon x, that is 1 upon y upon x is equal to log x plus constant, or x upon y equal to log x plus constant. Equation can be kept in this particular form. Consider problem number 3. Which says that 2xy dx plus y square minus x square dy equal to 0. 2xy dx plus y square minus x square dy equal to 0. Therefore, 2xy dx equal to minus of y square minus x square dy. And so, we can write it as 2xy upon x square minus y square equal to dy by dx. We will have to take x square common from numerator and denominator because it is the second order homogeneous, second degree homogeneous. So it is x square into bracket 2y upon x divided by x square into bracket 1 minus y square upon x square. X square gets cancelled. Let y upon x is equal to u. Therefore, y equal to x into u. Dy by dx will be x du by dx plus u. And substituting in the given equation, it will come out to be x du by dx plus u equal to 2u upon 1 minus u square. U on the left hand side should be transferred to the right hand side, and so we get it as x du by dx equal to 2u upon 1 minus u square minus u. Taking the LCM, it will be 2u minus u into bracket 1 minus u square upon 1 minus u square, which is 2u minus u minus minus plus u cube upon 1 minus u square. Finally, right hand side comes out to be u cube plus u upon 1 minus u square. This is in the variable separable form, so we will write it as 1 minus u square upon u cube plus u du equal to dx upon x. And for integration now, for integration probably we will require some adjustments on the left hand side. It is integral 1 minus u square upon u into bracket 1 plus u square du equal to integral dx upon x plus constant of integration. We will have to separate out the integrals over here by taking the partial fractions, but the second degree term will create problems. So we will first of all find out or rewrite the left hand side as 1 upon u plus something upon 1 plus u square, but we will assume the numerator of u as a and numerator of 1 plus u square as bu plus d. Cross multiply, so it is a into bracket 1 plus u square plus u into bracket bu plus d divided by u into bracket 1 plus u square, and this must be equal to the actual term that we have, 1 minus u square upon u into 1 plus u into bracket 1 plus u square. So denominator cancels. Multiply by the constants and separate out the terms. So it is a plus au square plus bu square plus du equal to 1 minus u square. So we can collect the terms as constant first, that is a plus du plus we have a plus b into u square equal to 1 minus u square. Comparing, we get a equal to 1, we get d equal to 0, and we get a plus b to be equal to minus 1. Just compare the coefficients as constant, coefficient of u and coefficient of u square. But we know that a is 1, so it is 1 plus b equal to minus 1, and therefore we get b as minus 2. This is the method by which the partial fractions are to be carried out. And once we get the values of a, b and d, the left hand side can now be substituted by these values, and so it will turn out to be rather the integrable form. So it will be written as integral a is 1, so 1 upon u, plus b comes out to be minus 2, so minus 2u plus 0 upon 1 plus u square du, equal to integral dx upon x is log x plus constant of integration c. As we separate the integral on the left hand side, it is integral du upon u is the first term, plus, rather we can take minus outside, it is integral 2u du upon 1 plus u square equal to log x plus constant. Integral du upon u will be log u, and again 1 plus u square, its derivative is 2u du, which is present in the numerator, so it will be minus log of 1 plus u square as the integral. It is integral f dash x dx upon fx integrated as log of fx equal to log x plus constant. Taking all the log terms on one side, we can write it as log of u upon x into bracket 1 plus u square equal to constant, that is u upon x into bracket 1 plus u square equal to constant. For simplifying the solution, of course we are required to eliminate u first of all in terms of y and x, that is y by x. But before that we will cross multiply, so it will be u equal to c into x into 1 plus u square, and therefore y by x is equal to cx into bracket 1 plus y square upon x square. So this will come out to be cx into bracket x square plus y square upon x square. 1x cancels, so it will be c upon x into bracket x square plus y square, and then we can cancel out x in the denominator, and final answer will be y equal to c into bracket x square plus y square. Now we will proceed to problem number 4, and problem number 4 is x plus y dy by dx plus x minus y equal to 0. So it is x plus y dy by dx plus x minus y equal to 0. Therefore x plus y dy by dx equal to y minus x, or dy by dx is equal to y minus x upon x plus y. Numerator and denominator both are homogeneous of degree 1, so take x common, so it will be x into bracket y by x minus 1 divided by x into bracket 1 plus y upon x. With the same substitution that y by x is equal to u, that is y equal to x into u, we can proceed with the solution. Of course you are required to write it every time, that is let y by x is equal to u, therefore y equal to x into u, or dy by dx is x du by dx plus u. Substituting, we get it as x du by dx plus u equal to u minus 1 upon 1 plus u. Transfer this u on the right hand side, so it is x du by dx equal to u minus 1 upon 1 plus u minus u. Take LCM, so it is u minus 1 minus u into bracket 1 plus u divided by 1 plus u. So it will be u minus 1 minus u square upon 1 plus u. U cancels and you will get the right hand side as minus into bracket 1 plus u square divided by 1 plus u, which is in the form of variables separable. So we can cross multiply and write it as 1 plus u divided by 1 plus u square du equal to minus dx upon x. Being variable separable, we can directly proceed with the integration. So it will be integral 1 plus u upon 1 plus u square du equal to minus integral dx upon x plus constant of integration. Left hand side, we cannot integrate it as it is. We will separate out the terms. Numerator has degree less than the denominator and denominator contains only one term. So to make it integrable form, we will write it as 1 upon 1 plus u square du, because we have a formula for 1 upon a square plus x square, plus integral u du upon 1 plus u square, and 1 plus u square can be differentiated. You will get numerator as 2u du, and that 2 should be adjusted. Whereas the right hand side is directly in the integrable form. It will be minus log x plus constant of integration. Integral du upon 1 plus u square is nothing but tan inverse u, plus the second term, it is half log of 1 plus u square. It is the same formula. Integral f dash x upon fx dx is nothing but log of fx equal to minus log x plus constant of integration. We can collect these two log terms, so it will be tan inverse u plus this log of half log of 1 plus u square. This half can be transferred as the power, so it will be log of 1 plus log of under root of 1 plus u square plus log x plus equal to the constant of integration. So it will be tan inverse u plus log of x under root 1 plus u square equal to constant. Now we can resubstitute value of u. We can resubstitute value of u as y upon x and rewrite the solution that we have obtained as tan inverse u, that is tan inverse of y by x plus log of x into under root of 1 plus y square upon x square equal to constant. When you take this x inside the root, it will be x square, so you are required to multiply by x square. The final answer is tan inverse of y upon x plus log of under root of x square plus y square equal to the constant of integration. And lastly, the problem number 5, which is homogeneous of degree 2. The given problem is y square plus x square dy by dx equal to xy dy by dx. You will have to collect all the dy by dx terms on one side. So we can write it as x square dy by dx minus xy dy by dx equal to minus y square. So it is x square minus xy dy by dx equal to minus y square, or dy by dx equal to minus y square upon x square minus xy. Both numerator and denominator are homogeneous of degree 2. So we can take x square common from the numerator and denominator, resulting in x square into bracket minus y square upon x square divided by x square into bracket 1 minus y upon x. So x square gets cancelled. With the same substitution, that is, let y upon x is equal to u, that is y equal to x into u. Therefore, dy by dx is equal to x into du by dx plus u. We can rewrite the given equation as x du by dx plus u is equal to minus u square upon 1 minus u. Take u on the left hand side to the right hand side. So it will be x du by dx equal to minus u square upon 1 minus u minus u. Taking the LCM, numerator is minus u square minus u into 1 minus u. So it will be minus u square minus u plus u square upon 1 minus u. U square cancels. And now this variable separable form can be rewritten as 1 minus u upon u into du equal to minus dx upon x, which is variable separable. So we can integrate both sides. So it will be integral 1 minus u upon u du equal to minus integral dx upon x plus constant of integration. To integrate first term, rewrite it as 1 upon u minus 1 du equal to, it is minus log x plus constant of integration. So it will be log u minus u equal to minus log x plus constant of integration. Combine these two log terms, so it will be log of ux minus u equal to constant, and resubstitute u as y upon x. Ux will be simply y, so it is log y minus y upon x is equal to constant, will be the solution of fifth equation.